pleasant morning for each and everyone. My name is Noveline Marquez Jacob from BSE3 Mathematics. So this video is all about instructional video in our subject number theory to be passed by Sir Noel Palapus for our final examination. So for today's video, I am going to discuss the ring in abstract algebra. So before we proceed, what is ring? So, a ring is a commutative group under addition that has a second operation which is multiplication. These generalize a wide variety of mathematical objects like the integers, polynomials, matrices, modular arithmetic, and more. So, why is it called ring? The name ring is derived from Hilbert's term Zahl ring or number ring, introduced in Zalberg for certain rings of algebraic integers. As for why Hilbert chose the name ring, I recall reading speculation that it may have to do with cyclical or ring-shaped behavior of powers of algebraic integers. Ring is where you can add, subtract, and multiply. Let's proceed to the examples.
Roughly speaking, a ring is a set of elements where you can add, subtract, and multiply. But you may not be able to divide, and multiplication may not be commutative. For example, the 2 by 2 matrices with real numbers form a ring, and matrix multiplication is not commutative. By not requiring multiplication to be commutative, rings generalize things like matrices, which are pretty important. By the way, did you notice I said elements instead of numbers? That's because some rings consist of numbers, while others are made of more exotic objects, like polynomials or matrices. Before we give a more precise definition, let's see some examples. The integers are a ring. You can add, subtract, and multiply any two integers, and you'll get another integer. But, can you divide two integers? Well, yes, but you may not get an integer. If you divide 3 by 5, you get a fraction, not an integer. That's key. If you add, subtract, or multiply two elements in the ring, you get another element in the ring. We say the ring is closed under addition and multiplication. What happens in the ring stays in the ring. Another example of a ring is the set of polynomials with integer coefficients. You can freely add, subtract, and multiply two such polynomials, and you will get a third polynomial of this type. But division? No, I don't think so. If you divide x plus 1 by x minus 1, you get x plus 1 over x minus 1. Hey, it's a thing, but it's not a polynomial. So now for the official definition. A ring is a set of elements with two operations, addition and multiplication. If you add two elements in a ring, you get another element in the ring. But earlier I said that you can add and subtract in a ring. What gives? Well, subtraction is just the same as adding inverses. So when I said you can add and subtract, I was essentially saying that rings have negative elements. And if you add an element to its negative, you get 0. So in a ring, the elements are a group under addition. Better yet, addition is commutative in rings. Now here's where things get serious. If you multiply two elements in a ring, you get another element in the ring. It's closed under multiplication. No surprise there, but elements may not have inverses under multiplication. We may not be able to divide. So while a ring is a nice abelian group under addition, things may not be so nice with multiplication. But hey, at least multiplication is associative. And to wrap things up, there's a rule which connects addition and multiplication, the distributive rule. All the numbers you studied in arithmetic obey the distributive rule. The expressions in algebra do as well. So we're good. This isn't something new. Ladies and gentlemen, I give you the ring.